A lecture on ML Type Inference number 2, Inductive Definitions. Here we acquire basic background, mathematical background of defining a language or defining a set inductively. The starting point of any formal analysis of typing or language property is to define the target of analysis. In this case, a language. Language here means abstract notion of some set consisting of some syntactic object, parse, tree, or string. So language is defined usually by a grammar. This is a typical example. In this case, ML expression, the part of ML expression. So in this grammatical definition, we introduce non-terminal, in this case exp, and then enumerate possible structure of this non-terminal. In this case, non-terminal can be a variable, constant, or function expression, or function application. So according to this grammar, 99, this string or this identity function expression are example of expressions. So I note that for an actual language definition, a number of additional rules, such as the lexical structure of this identifier and associativity of expression, are required. Now, our interest is not to define a concrete programming language in detail, but to analyze the essential property of typing. So in such theoretical analysis, or in a programming language theory, in this case type theory, a language is defined abstractly, omitting irrelevant lexical and parsing details. So for such an abstract definition of a language, we start by assuming given sets such as constants and variables, and introduce meta-variables representing these given sets. For example, for lambda terms, we assume the following sets and introduce meta-variables. Here set bar and meta-variable x. X means the representative of this set. And this is a countably infinite set of variables. Concrete example is such as x or f. And also assume a given set of constant. So we use meta-variable c of b, c superscript b, a given set of constants, like 99 or string SML sharp. Well, I note that this c of b indicates the type of constant c. This is used later in defining a type system. So for the moment, you ignore this b, but just a representative meta-variable. This whole thing is a representative meta-variable of this set of constants. Right, so we start this way. So we assume just variables and constant, and we do not specify its detailed structure. We omit these details. That is one starting point of formal definition of a language syntax. So once we introduce the given sets to start with and the meta variables, next step is to define grammar rules. So to define grammar rules, we also introduce a meta variable for each syntactic category. In the case of lambda term, we introduce meta variable e, and this e represents also the set, but in this case, set to be defined by the grammar rules. So let's call this set big lambda. Big lambda is a set of lambda terms to be defined. This corresponds to non-terminal. And then use B and F, Backus-Naur form notation of this form to define the syntax of the set that meta variable E represents. So this is the B and F notation. So you can immediately see that this B and F notation corresponds to the previous grammar rule using a non-terminal. Right? So E this is a meta variable, and you enumerate possible structure of the set being defined by E. And this corresponds to grammar rule in a previous slide, like X is the non-terminal ID and C of B. You enumerate possible structure of constant, and this is concretely written in this way, and this is also this grammar rule. So this BNF notation is the same as previous grammar rule, but this is an abstract syntactic definition. Here, in these notations, we assume that we abstract out the syntax, essential structure of the syntax, I mean, by omitting lexical and parsing details. So in this notation, we understood that structure of X and structure of this constant are assumed to be understood, and no further definition are given. That is the assumption. That is the abstract syntax definition by BNF notation. So purpose of today's lecture, today the video lecture of number 2, is to understand rigorously, mathematically, the property of abstract syntax definition. So to proceed, we briefly review objectives of definition. In case of concrete definition of a language syntax, there are many purposes, but the typical one is for compiler to parse, so parsing by a compiler. And object to be defined is a set of derived strings. In contrast, in the case of an abstract definition of a formal language syntax, purpose is theoretical analysis of types and other properties. In our case, type inference, so formal reasoning about the essence of type inference, various property of type inference, right? So object to be defined is a set of elements for mathematical reasoning. So in this chapter, or in this video, we study a framework for defining a formal language as a set of mathematically defined objects. So we start by reviewing intuitive understanding of a set to be defined by BNF notation. So to review intuitive understanding of the set defined by BNF specifications, let's consider the concrete BNF specification, this one. So as I explained, this E is a meta variable representing the set being defined by this very definition. And this right-hand side is the body of the definition. Right? In this case, this is supposed to define the set of lambda terms. So we call this set big lambda. And from the shape of this definition, you can see that this E occurs inside of the body of the definitions. So this is a cyclic form, or superficially at least. So we need to be careful about this form of definition. So we need to understand what's going on by this definition, right? So it is a good idea to reflect on the act of defining something. Mathematically defining some concept is simply to restate in terms of existing concept. But this doesn't have this shape because you use the concept itself inside of the body. So there are two natural intuitive understanding of the set being defined by this special form of definition. So let's review these two. The first interpretation is this one. BNF has a set of conditions on the set being defined, in this case big lambda. So this body, the four components are interpreted as follows. First, occurrence of X. X, as we understood, X represents a given set. And so this occurrence of X is interpreted that this set, big lambda, contains the set bar. This is a given set represented by X. So this condition on this set being defined. Similarly, for this constant occurrence. Constant, this symbol, this constant meta variable represent a given set const. So simply writing this constant, it is interpreted by this condition. The set being defined contains this set. These are just conditions, so no circularity obviously. And then these two occurring E inside. So this one is interpreted in the following way. If E is in lambda, big lambda, then the element of this shape constructed from E is also in this set. Similarly for this one, you have two occurrences of E, so the interpretation is this. If E1 is a member of gamma and E2 is a member of gamma, then element constructed from E1 and E2 is also a member of gamma. These are just a condition on the set, so there is no circularity, obviously. So this condition are well-defined, well-understood condition, no problem at all. And then in order to determine the set big lambda, there is a special condition, number 5. Gamma only contains the elements stated above. With this condition 5, the set big lambda is surely determined. Well, if you are completely satisfied with this interpretation, it's fine. You can go on, and that's one approach I already said. However, if you think a little bit more carefully, then something unnatural, something odd is going on. Now, 1 through 4 are conditions. So what do you mean by only contains the elements? So condition doesn't determine the set of elements, obviously. So there's something uncertain or ambiguous aspect going on. So let's see the second interpretation. The second interpretation is being as a set of rules to generate elements of this set, in this case big lambda. So the body of the definition is interpreted in the following way. So first component x is interpreted as follows. Add all the elements of this set represented by x to the set you are defining. Similarly, this component is interpreted as add all the elements of const represented by c, this constant meta variable, to the set being defined. And then this component is interpreted as if E is an element of this set being constructed, then also add this element. Similarly for this one, if E1 and E2 are already added in some sense, E1 and E2 are members of this set, then you add this new element to big lambda. Now, these are operation adding or generating elements of big lambda. So there is some special meta condition, condition 5, or specification 5, interpretation I would say. So this big lambda is a set obtained by applying the above generation steps, right? So you can see, or you can understand maybe that the set big lambda is surely obtained by these generation rules. But again, there is some ambiguous or some uncertain or whatever odd aspect. So, for example, when do you stop the generation steps? Well, you never stop, right? So infinitely many or something. Then another question that, do we really get a set? I mean, well-defined, rigid, I mean, completely determined set? This kind of question may arise. The purpose of this video is to understand rigorously about these two typical interpretations Well, I note that in many cases, one of intuitive definitions, one of intuitive understanding, I would say, would be sufficient to proceed. So usually we don't care about the detailed mathematical development, just assume that that's okay. But the following the policy of this lecture, that is explaining the essence clearly and rigorously, we study a mathematical framework that is inductively defined set and principle of induction. That makes the intuitive understanding clear and precise. I would note again that the mathematical development of inductively defined set that follows in this video is of course the basis of any logical analysis of languages, including type inference. However, you can follow most of the type inference lecture following this video lecture, video lecture of number 3 until number 10, without its detailed understanding, without a detailed understanding of this mathematical development of inductively defined sets. So you can postpone or skip the rest of this video. So this is just a note. But if you are interested, please continue listening. So in order to make this video self-contained, I introduce mathematical notation and notions. Usually, so this is quite standard. So let A1 through An be a set. We use the following set operations. So first, this one is NRE, Cartesian product of A1 through An, written this way. This is a set of tuple, A1, small a1 through small an. Each AI is taken from large A of I. And as a special case of this, where A1 through An are all the same A, we write A of N, right? This one of NAs. This is the NRE Cartesian power of A. Now we use notation functions. F be a function, dom F is the domain of F. And for subset of domain X, for subset X of domain, F of large X is a set, F of small x, X for any X in large X. And this notation is a restriction of F to X, right? More precisely, the function denoted by this graph, right? So this notation I sometimes use. Vertical bar x, small x, overline is a function which eliminates this point x from the domain. And this notation, f parentheses x1 colon v1 through xn colon vn is the new function f prime, such that domain of new function is the domain of f union x1 through xn, and f prime of y is f of y if y is different from any of xi, and f prime of xi is vi, right? So this is a function extension of these points, but note that xi can be an element of domain. In this case, this xi, the value of xi is changed to vi. So these are mathematical notation. So this is our answer to the question, what kind of mathematical set we get from recursive or superficially circular definition of BNF specification. That is inductive closure. So this slide is one of the highlights of this lecture. So let's go through this slide carefully. So let U be the universal set and F be the set of functions of the following form. For various n, F is a function from this set to this universal set. Namely, F takes up tuple of n element of this universal set and return an element of this universal set. So we call n a rank of f and write this way, rank parentheses f. We also use notation, this is just a notation, for an element of f whose rank is n. Now we introduce another notation for a subset x of u, large F of x. So f is a set and x is a set. So there is no function application. So this is just a notation, and this denotes this set. So this is a set of all elements for any f and corresponding tuple in taken from x, the result of this application. So we collect all the result of f applied to this tuple. Right? So using this notation, we define one notion. X is closed under f if f of large x is a subset of x. Right? So this is a condition that x satisfied. X is closed under f if this condition is satisfied. And then this is a major definition, inductive closure. So let C be a given set, given subset of U. The inductive closure of C under F, denoted by ind parentheses C comma F, is the smallest set that contains C and is closed under F. So this is the definition. Here smallest means the smallest set under the set inclusion relation. Right? So various set definition, sets defined by recursive or self-referring rules such as B and F specification are understood as inductive closures. This is our claim, and the rest of this lecture is to verify, precisely understand this claim. So in order to verify our claim we just made, so that the BNF-like recursive definition defines the set which is characterized as inductive closure. So in order to verify this claim, we state some property of inductive closure. First one is that this definition, this notation is defined as the smallest set containing C and closed under F. So this definition indeed denotes some set. I mean, this definition indeed exists. We need to verify this because set of sets may not have a smallest element. Right? In order to verify this, let X be a non-empty set of sets and define the operation big set intersection. Right? So set of X is a set of sets. So big intersection is any all element of A such that A belongs to Y for all Y such that Y is an element of X. Right? So this is a standard definition of big intersection, the standard generalization of intersection to find finite or infinite set of sets. Now C, so the definition of containing C, so this C by definition, by assumption, C is a subset of U, right? And this notation, you remember that this is the result of all application of any element of F to any corresponding n tuple taken U, right? This set is by definition is a subset of U because F is a set of function returning U, element of U. So by definition, this condition is satisfied. So this is by assumption. So the set of all sets that containing C and closed under F contains U and therefore non-empty, right? So you can take intersection. Also, it can be verified that the property of closed under F is preserved by this big intersection operation. Therefore, this definition exists as an element, as a set, and indeed that element defined by this is written this way. So smallest set that contains C closed under F is the smallest element of this set, which is indeed the intersection of all the sets in this set. So intersection belongs to. So intersection, we take intersection, then that is also a member of this set. So this is indeed the smallest element. So this ind C, F indeed exists. So I prepared the exercise of this video, exercise 1. The first one, item 1, is consider a proper definition of this big intersection when X is empty. Right? Second one, let big delta be a set of sets. Show that if each element of delta is closed under F, closed under F, then so is big intersection of delta. We use this property to establish this equation. Right? So I hope you enjoy this exercise. So next property of inductive closure is to characterize the definition. Now we understand that that definition exists. I mean, that the definition of inductive closure denote really the set, which is the intersection of all the set contains C and closed under F. Now we give another property of that definition, that is generative or generational property, I would say. So let's go through this. Define the set of sets xn. N is a natural number starting 0, defined in the following way. X of 0 is C, and then xi plus 1, I is any natural number greater than or equal to 0, is xi union f of xi. Right? So we understand this notation, right? So xi plus 1 is xi added with this new element. So you get a sequence of sets indexed by n. Now we have the following property on this set. This set is now defined, and we know that this exists and characterized as an intersection of all the set containing C and closed under F. And this set indeed can be shown that this set is equal to the big union of xi. I is equal or greater than 0. So this big union notation is just straightforward definition I omit. Right? So this is a proposition we need to show this equality. So we go through the detailed proof in the following slide. So this is an equation on sets. So standard way to prove a set equation is to show two-way inclusion. In this case, it is sufficient to show this inclusion and this inclusion. Right? So we show both of them. We first show this way of inclusion, this proposition. The proof is by this 5 steps. This is the proof outline. I will go through each of the steps. First, we establish that it suffices to show that this set, right-hand side of this set, is closed under F. If we can show this property, then we are done. This proposition follows. So let's check this. So suppose this is closed under F. Then, since this set obviously contains C because X0 is a C and closed under F. So this set is a member of this set. Now, this set, the big intersection, which is included in each member of this set. So in particular, this intersection is included, subset of this set. But by definition, this inductive closure is defined to be this one. So we are done. So first step is confirmed. So rest of the step 2 through 5 are to show this property. This set is closed under F. For this purpose, we pick arbitrary element from F, call this element F of n, and then depending on this element, we pick a tuple. We use vector notation from this set, nRE Cartesian power of this set, and then reason the following way. First, there is some case such that this vector tuple is indeed belong to some xk of n. Let's check this property. This is just a trivial property, but let's confirm this, right? So this tuple, vector notation, is indeed this form of tuple, x1 through xn. Each x1 through xn belong to this set, right? So by definition, this is a union. So xi belong to this set means there is some xki containing xi, right? So there is some k1 through kn such that this member, this xi, is in this xki, xk1, and xn is in xkn. But by construction of this set, so we take a maximum in the integer order, maximum of k1 through kn, k. Then by definition of recursive definition, inductive definition of this set xki, xki plus 1 contain xki. So this set is increasing order, increasing. So each xki belongs to xk, this maximum. So this vector, this tuple, belongs to xk of n. So this confirms this. There is some case such that this tuple is in this set. So now we apply this function to this tuple, and then we can see that this element belongs to xk plus 1 because this xk plus 1 is constructed in this way. So we have this component. So this component contains this one. So this element is in xk plus 1, which is also in this set because this xk plus 1 is a subset of this set. So we have done. Therefore, we have f of this set is a subset of this set. So we have completed the proof of this property. This set is closed under F, and therefore we have completed the proof of this property. So next we show the reverse inclusion, this proposition, right? So this is a bit simpler than previous inclusion. Let's go through the detail. So this proof of this, so this is a union of sets xi for I, right? So it is sufficient to show that for any I, xi is a subset of this, then union is also a subset of this, right? And then we show this property by induction on I, mathematical induction on I. So by as a basis, x0 is C. So this is by definition of this set is a subset of this set. So for the induction step, we assume that xi is a subset of this set. Since this is closed under F, this is also in this set. Since xi plus 1 is defined this way, and this is the induction hypothesis, by induction hypothesis, this is a subset of this set. And we showed that this part is also a subset of this set. So we have completed this induction step. So therefore we have completed this property, the proof of this property. So with this preparation, we are now in the position of defining the set of lambda term as an inductive closure. Nothing elaborate, nothing complicated occurring. So this is just a trivial process, but let's go through this in detail because this may be a first time you see this kind of thing. So let's go through this. So we take the universal set U as a set of all strings or a set of all possible parse trees or whatever your universe looks like, and define this set, big lambda, as the following inductive closure. In order to define inductive closure, we needed two components, right? C and F. So let's define F, the set of function. So for each x in this set bar, this is a given set, right? For each element in the set, we define this function, lambda, f of lambda dot x of arity1 as a function that returns from E this element. Given any E, return this element. And define arity2 function f(app) as a function that returns this element from tuple E1 and E2, because this is arity2. We now let this f subscript big lambda in this set, right? So this is a function for each x and then one function, f(app). So this is a set of function. And define this inductive closure, define this set big lambda as an inductive closure bar union const, comma, f of big lambda. So this is a complete definition without any circular notation. And my claim, so purpose of defining goes through this is that this mathematical definition of inductive closure indeed substantiate to intuitive interpretation of the BNF specification. So this is really a real purpose of going through this, so in some sense tedious mathematical development, usually ordinary textbook skips, but as we saw in the previous slide that both interpretation, like a condition, but condition number 5, special meta condition that set contain only those elements that generated above, something funny or something unclear, same as set of generation interpretation, iterative process, but when do we stop or something? So these ambiguous or some uncertainty are now clear up by this mathematical tool of inductive closure. So let's go through this interpretation with respect to this mathematical definition of inductive closure. The first interpretation, BNF as conditions interpretation. For this interpretation, we consider the property of inductive closure, this property, right? So this is the definition, defining property, right? So this set is the intersection of set of all those set containing this. Parentheses, this parentheses is around this, so bar and const is a subset of V, right? So I should have put the parentheses here and here, but you can understand this, right? And then this set is closed under this function, right? So we will take big intersection. So this equation states that this big lambda is a superset of this bar and const, right? And then this big lambda is closed under this function, right? It is closed under this function and this function. So this big lambda is the smallest set, so third one, so big intersection is the smallest set satisfying this and this condition. Now, smallest set is a trivial property. Nothing mysterious. Just take a intersection. And in this case, smallest set exists. We saw that. And so we can take the intersection. And then by the definition, this intersection is the smallest set satisfying 1 and 2. So this is a mathematical property we can see. And interpretation of BNF as condition, right? We saw before that condition interpretation is this condition and this condition, and then these two conditions. If E is in lambda, then this element is also in lambda. E1 and E2 are in lambda, then this element is also in lambda. Is nothing but that this lambda is closed under this function and this function. And so mysterious condition 5, gamma only contains elements stated above, is clearly substantiated by this big intersection, that this set is a big intersection satisfying this and this. So this mathematical property substantiate BNS as condition interpretation. We are now comfortable with this, interpretation. So to substantiate BNF as generation rules interpretation. So in this case, we consider the other equation we have just proved. That is this equation. This set is, we proved that equal to this set of union of all xi. So this equation, this mathematical equation states that big lambda is the union of the sets generated by the following operation, starting with x0 of this set, and for each xy, so you make a new element, this one, and the resulting element is added to xi plus 1, and iteratively generate the sets. So you get a set indexed by natural number. And then we take big union, right? So this mathematical property is indeed substantiated this BNF as generation rule interpretation. That is, add to big lambda this given set, same as this given set. And if E is added to lambda, then you also add this element. Two elements are already added, then you add this element. And mysterious condition 5. Lambda is a set obtained by applying the above generation step infinitely many, is indeed intuitive understanding of the above mathematical property. Because now you don't, this is a natural number. This is a set indexed by natural numbers. Every element is just defined, right? So you can safely take a union, no problem. And I would note that, so this construction, this equation, we proved. So this set of union is merely the union of the set indexed by natural numbers. We do not need any elaborate notion such as fixed point or continuous function and so on. So this is just an elementary set operation, elementary reasoning of a set. And so you don't have to worry about when we stop at this generation step, or do we really get set? Well, so this set is mathematically simple set by taking a union, right? So this is the end of this today's No.2 video's lecture.